My name is Rulin Van Dyke. I'm with Agilent EESOF, and here to talk about large number of simulation of large number of carriers. This is an innovative technique that we have just developed, and it allows users to simulate hundreds of carriers in a fraction of a second. Traditionally, this is something that has been difficult for the TV industry to simulate large number of carriers. Generally, they just worry about in-band. In this particular case, we're going to look at broadband simulation. All right, a few basics first. If we take just a simple nonlinear amplifier where we have power input versus power out, we get the green curve at the top. And if we were to go ahead and put a single carrier tone into this amplifier, we see the picture over here on the right. The blue signal is the amplified signal, and then the little red vertical pieces are the harmonic spectrum. So we see a second harmonic and a third harmonic and also a DC component. And engineers are very familiar with the two-tone analysis, where we put in two tones, and then of course we get the third order intermods that are just right next to the two blue carriers, and then of course the second harmonics, the third harmonics, and then we get sums and differences of all those. Well, so what do we do when you put in 100 or 200 carriers? How do you simulate that? And this has been the challenge in the cable TV industry for years. So we have come up with a technique to solve this particular problem. If you're familiar with harmonic balance is a great circuit analysis tool. And this is a particular setup, but here you see a typical simulation of 5 carriers around 6 seconds. And for 10 carriers, it's over 500 seconds. Now, harmonic balance is a great circuit simulator, but it's just really not optimized to solve this particular problem. And of course, there's things that you can do with harmonic balance to get that speed up to make the carriers harmonically related. So some of the challenges are the complexity, just the sheer number of intermods that you have to calculate and that you have to manage. And because there's so many intermods that you need to manage, the memory size goes up, the simulation speed is slow, and you just have to manage all these objects and keep track of them in a simulator. So here's a little simple example. This is just second and third order nonlinearities, and what we see is we've got the number of carriers on the x-axis, and so you can see there 5, 10, 15, 20, and so forth. That is the number of carriers. And then the box below that on the x-axis is the number of intermods that it takes to simulate that number of carriers. And then there in the red square, you see that if we were to put in 200 carriers, that it would be 5 million intermods. And this is just for one nonlinearity. And this is why it's been very difficult to manage for anybody like the cable TV industry that are really trying to simulate large number of carriers. So, and in real systems, I mean, how often do you just end up with one nonlinearity? I mean, that's not very practical, right? There's lots of nonlinearities in the whole system. So, this is a simple illustration, and I'll talk a little bit more about this later, but what we see here is we've got 10 carriers, and what we're really interested in is keeping track of the envelopes, not so much the individual intermods. The individual intermods here are shown by the purple and the blue, or the purple and the red lines. The purple ones are the 2x1 products, and the red ones are what is commonly called the composite triple beat. And so there's several intermods that fall at the same frequency when you have multiple carriers. And so these intermods add up, and then we get this total trace that you see, this total envelope. And so the carrier triple beat would be the signal level, the red shape there in the middle of the graph. All right, now so this is a more detailed explanation. And we're just going to look at 5 carriers here, and their carriers are labeled 1 through 5. And once again, these are the blue signals. The red signals are the intermods that are being generated. And so we're just going to look at one intermod group. This is the 1 by -1. This is what they call the composite triple beat. And so it's carrier 1 plus a second carrier minus a third carrier. And that's the only intermod that we're looking at in this particular slide. So if you were to look right underneath carrier 1 there, there's a gray box off to the left. And those are listing the combination of carriers that generate a particular intermod. So on the very left, under the first carrier, there's 5 intermods that are generated. 1 plus 2 minus 2, 1 plus 3 minus 3, and so forth. Under carrier 2, 3, and 4, we have 8 intermods being generated. And under carrier 5, we have 5, and then you can see some of the ones out of band. Well, when we add up these signals non-coherently, we're going to get a total. Now, what I mean by non-coherently is that it's assumed that these carriers are all, and the intermods are just a little bit out of phase. And so when they add, they're going to add in power. So we can make an assumption here that or a simplification, where we use equal amplitudes. And if we were to go ahead and look at the coherent case, if we made all the signals coherent so they have the same phase, then what happens is the composite triple beat gets a lot worse. And so you really want non-coherent carriers when you want to improve the intermod performance. All right, and so this is a plot of the actual simulation output. So what we're showing here in this graph is we're not showing the individual intermods. In this particular case, we've got 25 carriers, and what we're showing is the individual intermod groups. So we see right underneath the carrier, we have the composite triple beat, which is the 1 plus 1 minus 1. Below that, the gray shape there is the 2 by -1. These are what we would generally call the third order intermods. But the 1 plus 1 minus 1s are also third order intermods. And then off to the left, under the red, you can see the second harmonics, but the 1 plus 1s have higher amplitude than the second harmonics. And if you're to move off to the right, you'll see the third harmonics and the 2 plus 1s intermods, and then the 1 plus 1 plus 1 intermods. And then, of course, we've got the signals down at DC. All right, and so this technology is implemented in a product called Spectrasys, and that is available in Genesis, in System View, and also linked to an ADS. All right, and so here's some of the comparisons. On the upper left, you will see just individual intermods, and this is what it would look like if we tried to keep track of all the individual intermods and we add them up and manage them. We see the information at the left. But if you look at the lower right, all we're managing is envelopes. And so it's very easy to understand exactly what's going on in the system with the high carrier count intermods. And so readability is a lot better. Here's a graph where we talk a little bit about speed ups that I did. And so I compared this to the traditional method, which is simulating individual intermods versus simulating intermod groups. And so I've got circles over here on the axes because the scale is different. It would be pretty boring if on the lower right, if I had the same scale, it just looked like a horizontal line. Okay, but what you'll see here is that for 100 carriers, that it took almost 300 seconds to simulate. Over here, with the new approach, it's about 0.2 seconds. So it's very fast. And if you look at 200 carriers, it's under a second. Okay, so this is very quick. Also, if we just did a study of the file analysis, so we just took the simulation, we just saved it to disk, and that we see that at 100 carriers, we get 330 times improvement in file size. So the file size is a lot smaller. Also, you know, you have to display these intermods on a graph, and you've got to manage them. So this is the number of graph objects that you have to manage and display on a graph. So you can see that it's way over 1 million for 100 carriers, and it's constant in the high carrier count intermod case, because we're just simulating the same number of groups, we're just displaying the same groups. All right, and here's just an example where if we have 200 carriers, just the center frequency alone, there's about 15,000 intermods that you've got to manage and keep track of. And that's very complex and takes a lot of time. Here's a little simulation that I did where I took an IS-95 CDMA waveform, which is the blue trace, digital modulation. And then what I did is I represented that modulation with, I believe it was 20 carriers, and I used the high carrier count intermod simulation. And sure enough, what you see is the ACPR. I don't know if you can see the color differences there, but there are colors underneath the carriers there where you see the carrier triple beats, and then you see the 2x1 intermods, and you see that it lines up pretty well. And this is fast. All right. Once again, you know, in the cable TV industry, generally they're interested in in-band. Well, this is broadband, so we can look at wideband spurious analysis. The other great thing that we have is we have spectrum identification and root cause analysis. So you can put your mouse right over the spectrum, and a tooltip pops up, and it shows you the power level, the frequency. It gives you an equation, so it tells you who created it, and then the string of names at the bottom is the path that it took to get to your viewing destination. So you can actually identify the intermods, find out who generated them, and how they got to your destination, making this a great technique for debugging. All right, and here's a little video, and this is all real time. What we're going to do is we're simulating a UHF block. This is 200 carriers, and this is simulated in real time, and we're done. And so you see the intermods out to about 3 gigahertz. And so as you mouse over this, you'll see the carrier block. And then we're going to go down and look at the 1+1 intermods. This is now the second harmonic. This is the composite triple beat, the sum products. This is the 2+1s, and this is, there's the composite triple beat underneath the carrier, and then of course we have differences. Now what we're going to do, this is all non-coherent. Now what we're going to do is we're going to lock all of these carriers in phase. And so we're going to go ahead and add a reference clock. And then of course, when we run the simulation, these carriers are all going to be coherent. And so the intermods get a lot worse. Now what we're going to do is we're going to simulate the real US cable TV band. So there's a UHF block, there's a VHF block in a couple of different places. Now that just occurred in real time. So there's the UHF block, there's a couple of the VHF blocks, and what you see in the colors there are all the intermods that are being generated by those blocks, and all the intermods generated in all the groups. And if we took time, we could go through and see all of the intermod combinations, and the green line there is the noise, and it's also the total there that you see. That, you know, so all the intermods are kept track of individually, and then we sum them up to give them a total. Like a spectrum analyzer. On a spectrum analyzer, of course, all you're going to see is the total. But herein, with this technique, we can actually show you intermods underneath intermods, and we can show you signals underneath the noise floor. And really to help the RF engineers debug the problem and figure out what the problem really is. All right, so the benefits of this technique is broadband spurious analysis. It's very fast. If you're doing cable TV, maybe payload simulations where you need a large number of carriers. If you want to do any type of effects by using a frequency comb. It's very common to do a noise power ratio test where you have several carriers, and then usually you drop a few carriers and measure the intermods so you can see what the intermod level is, and that's very common. But with this technique, you can see the intermods underneath the signals. You can get in-channel signal-to-noise ratio, which is a great benefit and provides fast estimation of the adjacent channel power. So we get fast speed up, file size reduction, easier to graph, easier to read, better debugging capability, and this is broadband analysis. All right, thank you.